In this lecture, we will continue our discussion of the various properties of the Fourier transform. To start with, let us consider the signal x of t be a voltage signal. Okay. Now, let us imagine such a voltage signal is given to a 1 ohm resistor. Okay. Then, if x of t is periodic, then the power dissipated in this 1 ohm resistor is where limit t goes to infinity 1 over t naught integral of minus t naught over 2 to t naught over 2 x square of t times dt. Okay. So, this is called the power dissipated by the signal, or sometimes we refer to as power available from x of t. So, this is a periodic signal, and we saw that this quantity that is the power available from the signal, it can also be obtained from the Fourier coefficients. This we already proved. So, this will be equal to summation of Cn, you take modulus of this and square it, where n ranges from minus infinity to plus infinity. Either you calculate power using this x of t, or you can calculate using Cn. Okay. So, this is the relation which we already discussed when we talked about the Fourier series expansion of periodic signal. Now, what we would like to see is how this concept can be extended in the case of x of t, which is not periodic. So, this we have already seen. Now, let us consider the A part is periodic and the B part is aperiodic. If x of t is aperiodic, then how this concept can be extended. Now, we also assume that it has got a finite amount of energy. Aperiodic, let us assume that it has finite amount of energy. Okay. So, in the sense that if you integrate x of t, take modulus of this from minus infinity to plus infinity, then this is going to be give you a finite value. That is what we mean by finite energy means. Okay. So, this is a restriction which we already imposed on finding the Fourier transforms. So, whenever you have non-converging functions, then you cannot find the Fourier transform. Okay. So, we also assumed that you take x of t and square it and integrate from minus infinity to plus infinity. This also finite, this is also we already assumed. Okay. So, this is also true for an energy signal. If this is true, then you divide by t naught, 1 over t naught, and then you allow the t naught to go to infinity, then the power becomes 0. Okay. Because the numerator, this is going to be finite. I am sorry, hold on one second. This is finite. So, what we are saying is, then limit t goes to infinity 1 over t naught integral of minus infinity to plus infinity x of t modulus square then dt, which is equal to what? That is what the next question is. That means limit t goes to infinity 1 over t naught multiply by some finite quantity, right? It is some finite value. Then what will happen? Numerator has finite value and the denominator has t naught, where t naught goes to infinity. Therefore, finite value divided by infinity becomes 0. Therefore, the power becomes 0 for aperiodic signal. Okay, that is what we mean by. So when we talk about aperiodic signals of this type, where the square of the integral over the infinite time is finite, see this is finite over the infinite time, then there is no meaning in talking about power, because power becomes 0. Okay, so all that we can do in such a cases is only calculate the value of this integral, let me write down here, value of this integral and dt, and this has a dimension of energy, because this is a voltage signal, voltage square times time, therefore it has a dimension of energy, because we are not dividing by T naught, and this energy is non-zero, it is finite value. So this is nothing but energy available from, this is nothing but energy available from the signal. Energy available from the signal. So when we talk about aperiodic signal, it will be more convenient for us to talk in terms of energy available from the signal. Therefore, we will have this particular heading for this topic. So that is energy conservation. Okay, so in the case of aperiodic signal, we talk about energy. In the case of periodic signal, we talk about power, periodic power, aperiodic energy. Okay, so we would like to see what is the energy available for the signal in terms of Fourier transform. Okay, in terms of time domain, no problem, we have the relation. See, you have the source, and the source is given to a 1 ohm resistor, and the energy available is x of t, you take modulus and dt and integrate from minus infinity to plus infinity. So no problem as far as time domain is concerned. Now we would like to see what is the energy available for the signal in terms of its Fourier transform. Okay, so the energy dissipated in this 1 ohm resistor is given by this formula. Okay, now there is a square term here. So if it is a real signal, then instead of putting mod, I can put x square of t times dt. This is the energy. Now I can write this as x of t multiplied by x of t times dt. I can write like this. Okay. Now for this x of t, I use a inverse Fourier transform. What is inverse Fourier transform? X of t is equal to 1 over 2 pi integral of x of j omega e to the j omega t d omega. Okay. So integral of x of t, then this is going to be 1 over 2 pi integral of x of j omega e to the j omega t times d omega, and both the integrals, the range is from minus infinity to plus infinity. Now I would like to interchange the order of integration. That means instead of integrating in the w domain first, omega domain first, and then later on the time domain, I would like to reverse the roles. So I would like to integrate this whole expression in terms of time domain first and then frequency domain later. So therefore this 1 over 2 pi is constant, you can pull it outside. Then x of j omega is constant as far as time domain integration is concerned. Then integral of x of t, then e to the j omega t times dt, and then d omega. Now first finish out this guy alone. Okay, all terms involving omega which do not involve time can be brought outside here, this guy. Therefore 1 over 2 pi has come outside and x of j omega also has come outside. Okay, and this d omega also outside. Now let us look at this guy. Okay, if it had been integral of x of t e to the minus j omega t times dt, then no problem. This is, we can write as x of j omega, but instead of minus I have plus sign here. Look at here, there is a plus sign, positive sign. So just rearrange it. Okay, so instead of minus j omega here I have plus j omega t. So this whole expression now becomes x of minus j omega. How? 1 over 2 pi integral of x of j omega integral of minus infinity to plus infinity x of t e to the minus j minus omega times t, then dt and d omega. Now what is this? This whole thing is going to be x of minus j omega. So 1 over 2 pi integral of x of j omega times x of minus j omega and then d omega. Okay, so and the limit is from minus infinity to plus infinity. And as we already observed that for real functions, if x of t is real, this property we already discussed, real, then x of minus j omega is the same as x conjugate of omega, x conjugate of j omega. So for real signals, 1 over 2 pi integral of x of j omega multiplied by x conjugate of j omega d omega, x of j omega multiplied by x conjugate of j omega, that is going to be 1 over 2 pi integral of x of j omega modulus squared then d omega, and the limit is minus infinity to plus infinity. Okay, now what is the left hand side? We started with integral of x of t modulus squared and dt and minus infinity to plus infinity. So this is the energy available from the signal x of t. The same thing would be equal to energy in terms of the Fourier coefficient density function x of j omega. So the energy available from the signal is given in the time domain using this guy, okay, in this fashion, and in the frequency domain this one. The right hand side is frequency domain, the left hand side is time domain. Both are equal. Okay, therefore x of j omega modulus square can be thought of as energy density. Can be thought of energy density. So this is the energy density which is expressed in terms of joules per hertz. What it means is around a band or around omega, if you consider a small band of frequencies delta f, then f of j omega magnitude square times delta f gives you the energy concentrated in that band. Suppose you have the like this is your x of j omega, then you consider a small band, that let us say delta omega or delta f, whatever it is, let me say delta omega. Then this is going to be the energy available from that. You take x of j omega magnitude square then delta omega, that is the total energy, and that energy is concentrated near in this band with width of delta omega. So in a small band of frequencies centered around omega, then x of j omega square times delta omega by 2 pi is the available energy. Available energy in a band delta omega, centered around, the band is centered around what? Where? Omega. Therefore, to find the total energy, you have to sum up all such energy in the different bands, so that it becomes the integral. Okay. Therefore, the total energy you can calculate either in the time domain or in the frequency domain. In the frequency domain, it is 1 over 2 pi x of j omega whole squared times d omega. And this is an interesting relation. Okay. So, this is of course equal to integral of x of t mod square and dt, and the limit is from minus infinity to plus infinity. So, both are equal. Let us say this is 1 and this is 2. So, you can calculate the energy in the time domain. You can also calculate the energy available from the signal in the frequency domain using equation number 1. Either way, either equation 1 or equation 2. But what you have to do is you have to multiply this guy by 1 over 2 pi and integrate with respect to d omega over the whole range of frequencies from minus infinity to plus infinity. You get the total energy that is available from the signal. And these two relations for aperiodic signal. What is the relation for periodic signal? 1 over t naught integral of minus t naught by 2 to t naught by 2, then x squared of t and dt. This is equal to summation of Cn mod square, n is equal to minus infinity to plus infinity. What is this? This is the power, and this is for periodic signal, and this is energy for aperiodic signal. So, these relations are usually both, let me call this is 3 and this one is 4. Therefore, equation 1, 2, 3 and 4, these 4 equations are usually referred to as Parseval's relations. Equation 1 and 2 is a Parseval's relation for aperiodic signal. Equation 3 and 4 is called Parseval's relation for periodic signal. It is also occasionally called something called Plancherel's theorem. Plancherel's theorem. Okay, so it is proved by Michael Plancherel. He is a mathematician. Okay, so the Parseval's relation in the case of periodic signal is in terms of the Fourier coefficients. In the case of aperiodic signal, it is in terms of an integral involving the energy density over minus infinity to plus infinity. Okay. Now, so in this lecture we talked about an aperiodic signal with a finite amount of energy. Then you can talk about then you cannot talk about power available from the signal, which is going to be 0, because the base t naught, this t naught, if it goes to infinity, then you will be in trouble. So, it will become 0. The average power over the complete time period is 0. So, you can talk about only energy for the aperiodic case. And the total energy available from the signal can be computed in 2 ways. One is in the time domain expression and another one is in the frequency domain expression. Okay. So, suppose if you write x of t and take modulus and dt, what is the meaning of this? This is a voltage signal. Let us say voltage signal x of t is a voltage signal, as I said. Then x squared of t, that means voltage squared, and multiply by time. So, this is going to be energy, and it is through 1 ohm resistance. Okay. Therefore, this whole thing gives you energy that is dissipated in that 1 ohm resistor. You can calculate either in the time domain or in the frequency domain, as the case may be. Now, let me consider some example. So, let us take x of t is equal to e to the minus at times u of t, right. Now, let us calculate energy of x of t. Okay. So, this you can do again by 2 methods, either in the time domain or in the frequency domain. Let us try to calculate in the time domain, and then later on we will move on to frequency domain. In the time domain, energy available or available energy is equal to integral of x squared of t if it is real signal. If it is complex, then you should take modulus dt, right? So this is integral of e to the minus at, no need to take modulus, minus infinity to plus infinity times dt. So this is e to the minus 2at integral dt. So e to the minus 2at divided by minus 2a, and the limit is this guy. So if you solve this, then you will get 1 over 2a joules. So this is the available energy from the given signal. Now let us do the same calculation in the frequency domain. So what is the Fourier transform of e to the minus at times u of t? It is x of j omega. What is x of j omega? X of j omega is equal to 1 over a plus j omega. This is my x of t. Now in the frequency domain, the energy is total energy available from the signal is 1 over 2 pi integral of x of j omega. Now you take modulus. Why? Because it is complex. If it is not complex, no need to take modulus. Okay, take modulus and then square it. Integrate with respect to omega, and the range is minus infinity to plus infinity. So 1 over 2 pi, then you take modulus and square it, then it become a squared plus omega squared and then d omega, and the limit is minus infinity to plus infinity. Now this is standard integration, so you can straight away write down the result. So 1 over 2 pi, this is 1 over a tan inverse of x by a, and apply the limit minus infinity to plus infinity. So again you will get 1 over 2a joules. So I skipped the substitution, or else you can say 1 over 2a pi, the limit is tan inverse of infinity, sorry this is not x, this is omega, minus tan inverse of minus infinity. Minus of minus becomes plus because tan is an odd function. So tan inverse of infinity is pi by 2 plus pi by 2, pi by 2, pi by 2 becomes pi. So 1 over 2a pi times pi, and pi will get cancelled. So again 1 over 2a joules. So the same answer what we got from the time domain expression. Okay. So now let us try to plot this x of j omega square term. If you try to plot, then it will be like this. When omega is equal to 0, the maximum energy, maybe the plot is symmetrical, then like this. When omega equals 0, then the energy will be, energy density function will be maximum. Okay, now this is a function of omega, and let me call this as square like this. You will get a curve like this. So this gives us an idea where the energy is concentrated. So where the energy is concentrated, at what frequency band has more energy. See, this frequency band has more energy. If you take this frequency, less energy, this band. Okay, so as we can see, there is a lot of energy in this region. Okay, in the lower frequency band, when omega equal to 0 or close to this range, this is low frequency band. In the low frequency band, you have more energy. In the high frequency band, you have less energy. High frequency band, you have very less energy. Okay, just reverse. So this additional information is obtained if you do the Fourier transform analysis as compared with the time domain analysis. So this kind of information you may not get it if you do the analysis in the time domain. Okay. Now let us see how this such a concept can be made use of in practice. Let us assume that this particular signal x of t, okay, is put through an low pass filter, and the output is, let me denote by x naught of t. This suffix o indicates output. and this input is, let's say, xi of t. Okay, now we want to know how this output will be and the amount of energy it contains. Let's say the characteristics of your low pass filter is like this. It allows from minus a to plus a, and this is your frequency omega, and let's say the magnitude is 1, and this is your frequency transfer function and magnitude of this. So a low pass filter essentially allows all frequencies up to this frequency plus a, and then it shuts off after, if omega is greater than a, then it shuts off all other frequency components. So let us imagine that our low pass filter here has a cutoff frequency equal to a and minus a. In other words, your h of j omega passes all the signals without any trouble, without any what you say, attenuation, when mod of omega is less than or equal to a and 0 otherwise. Okay, so essentially what we are doing is, you are taking the low pass filter, you are taking the low pass filter, and the low pass filter has the characteristic stuff like this, and it allows from minus a to plus a, and this is your input frequency, signals spectrum. Okay, now what happens, it allows only that portion from minus a to plus a. If you try to plot, it allows those portion only, it will not allow the rest of the portions. It cut off. Okay, it cuts off all frequency components beyond the value a. So as far as the output is concerned, your x naught of t corresponding energy density would be the one which contains frequency components within this band only, minus a to plus a. Okay, suppose I want to know what is the energy available in this let's say x naught of j omega. How do you calculate? Simple, very simple. Okay, so you have the relation, and you can very easily calculate it. Okay, because your output is nothing but input multiplied by this one, it is unity. Okay, therefore this energy is going to be 1 over 2 pi, and the limit is from minus a to plus a, then your x of input I, x of j omega modulus square and d omega. So 1 over 2 pi integral of 1 over a square plus omega squared and then d omega. Okay, again use the same calculation, then finally you will arrive with the 1 over 4a joules. So this is this much amount of energy present in the signal. Okay, so by making use of a standard substitution, you can get the result. It means that the output out of the total energy available from the input signal, see, from the input signal the total available energy is 1 over 2a, and the output energy is 1 over 4a. Okay, so half of the energy resides in the frequency band from omega is equal to minus a to plus a. So half of the energy is stopped by the low pass filter. Since when signals are transmitted through a linear system like a low pass filter, and these systems are characterized quite nicely in terms of the system function h of j omega. By the way, this is called system function. And if you like to find out the properties of the signal that comes out of the system or the response of the system, then frequency analysis in this manner turns out to be a very convenient tool, because filters like this low pass filters are characterized in terms of their frequency response, not in terms of their time response, and therefore the energy available from the output signal x naught of t can be conveniently handled. conveniently handled in the frequency domain. In terms of frequency. Okay, so if you want to do the same analysis in the time domain, then it will be much more difficult, because you have to characterize the filter in terms of its time response. Okay, it can be done, but it is much more complicated. But in the frequency domain, it is very easy to find out the response. Okay, it's very easy to design and easy to analyze. So this example illustrates how we can utilize the energy concept, and also how to find out the characteristics of various signals when you pass it through a filter. Fine. So far we have been talking about signals with the finite energy. As I said, finite energy for a periodic signal. Okay, with finite energy content and signals which are absolutely integrable over the infinite range. So even though you integrate from minus infinity to plus infinity, but this guy always gives the finite value, then only you will say it is a finite energy signal. You might recall that I mentioned earlier that we can extend the concept of Fourier transform to signals which are not absolutely integrable over infinite range. See, this is absolutely integrable. If it is a finite value, then you say it is absolutely integrable. But the beauty is you can use Fourier transform to find the Fourier transform concept to signals which are not absolutely integrable over the infinite duration. Sometimes you take a signal x of t, and the signal is, if you integrate, then it is going to infinity. In that case of signals also, these kind of signals also, these kind of non-absolutely integrable signals, non-absolutely integrable signals also can be used to find its Fourier transform. Okay. So for example, let us say x of t is equal to u of t. Now in the case of u of t, it is not absolutely integrable over the infinite range. Okay, so whenever you have a signal which are not absolutely integrable, then you can extend the Fourier transform concept to find its Fourier transform. Okay, similarly, you take a sine of omega ct times u of t. These are all some examples, and the cos of omega ct times u of t. Okay, so whenever you have the signals of this type, then the Fourier transform provides Fourier transform provides to use the impulse functions. Okay, so whenever you have this absolutely integrable, then in that time we use the impulse function del of t or del of omega. So anyway, that we will discuss very detail in the following lectures. Okay, so these kind of signals are justified from the theory of distributions in mathematics. It's a separate topic, theory of distributions in mathematics. So we would now like to familiarize ourselves with some other operational rules involving such functions. Anyway, we will not go with deep mathematical details of this theory of distributions, but still we will just assume some results and use them to derive the Fourier transform of signals whose energy content is not necessarily finite, okay, or necessarily infinite. Okay, so therefore in the next lecture, let us try to use a little bit about this theory of distributions in order to derive the Fourier transform of the signals. okay, where the signal's energy is not necessarily finite. Okay, so let me stop at this point. In the next lecture we will start this some useful relations, and then we will continue from there onwards. So let me stop at this point. Thank you very much.